Hello everyone. In today's video, we are going to continue our topic of chapter 17.2, which is on area between a curve and axis. In our previous lesson, we looked at finding the area of a region above the x-axis, and that is our definite integral of the equation of the function from a to b depending on what you are trying to find. In our lesson today, we are going to first find the area of a region below the x-axis, as well as to find the area of a region bounded by a curve and the y-axis. Now, we will first take a look at the area of a region below the x-axis. In order to find this area, we will continue to be doing a definite integral from a to b depending on the values that you're given. However, because we are looking at the area of a region below the x-axis, we will have to apply the negative sign to ensure that the area that we find is going to be positive in value. Let us first take a look at this example, where the diagram shows part of the curve y equals to 1 minus 1 over x squared, and the lines x equals to 0.5 as well as x equals to 5. We want to find the area bounded by the curve, which is 1 equals to 1 minus 1 over x squared, the x-axis, and the line. Okay, so the line that we have to first look at in part I is x equals to 0.5. So if you're looking at the area bounded by the curve, which is here, the x-axis, which is here, as well as the line, this is the area that we are first going to be looking for. Then in part 2, we will apply our understanding and see that the area that we're going to be looking for is over here. So let's proceed with going through the answers. So in part I, to first find out the area of the shaded region here, we know that this value is going to be 0.5, while this value is going to be 1. Furthermore, it is an area under the x-axis. So therefore, we have to apply a negative sign for our definite integral. So we are going to do our definite integral from 0.5 to 1. It is always the smaller value at the bottom, while the bigger value is at the top. For the equation 1 minus 1 over x squared with respect to x, and then we do our integration, substitute in the values accordingly into the expression here, and we will get 0.5 units square. For part 2, our working should not be unfamiliar to you because it is just the area of the region above the x-axis but under the curve. So we will do our definite integral from 1 to 5 for the equation of the function, which is 1 minus 1 over x squared with respect to x, and then we will substitute in the values, and we have 5.2 minus 2, which is equals to 3.2 units square. I want us to remember that we have to put in the units, okay, because in this case, there is an application for, or rather there's a context of finding out what is the area. We will now move on to take a look at exercise 17.2, question 8, that is in your textbook, page 132. So in this question, we want to find the sum of the areas bounded by the x-axis and the curve y equals to x times x minus 2 times x minus 3. However, the thing about this question is that there is no diagram given to us. So what can we do about it? Before we proceed with the question, I'd like to highlight an amendment that I'd like to make to this question so that it makes more sense. Okay, so the amendment that we like to make, or rather I like to make, is that I want you to include this boundary, okay, of x to be between 0 to 3. Otherwise, this curve actually goes indefinitely along the x-axis. Okay, so there is a need for this boundary in order for us to solve this question. Okay, so earlier on I mentioned that there's no diagram given to us. That shouldn't be an issue because we do realize that y equals to x times x minus 2 times x minus 3 is going to be a cubic function. And we should know the graph, okay, how the curve looks like for a cubic function. And that is actually in this diagram over here. Okay, so do observe that if I were to expand out this equation, I will be getting y equals to x cubed minus 5x squared plus 6x. And having such a expression, a cubic equation itself, my curve will have to look like this. Okay, for cubic functions, there are actually many ways our curve could look like. Okay, so just to do a very quick very quick recap, right, about cubic functions. If my coefficient of x cubed were to be negative, so let's say if it's a negative x cubed minus 5x squared plus 6x, okay, then my curve will actually have to look something like this. Okay, but take note that it's not a sine curve, yeah. Okay, it is actually going indefinitely like that, right? Likewise, for this cubic here, it is going indefinitely like that. Okay, so this is how cubic curves generally look like. However, there's also another type of cubic curves. Those are if I were to have, let's say, y equals to x cubed. Okay, so just solely x cubed only. There is no like quadratic expression along with it. Okay, so therefore, in this case, your curve will look like this. Okay, so let me draw in the axis. While if I have y equals to negative x cubed, then my curve would be looking like this. Okay, so I hope that this is a quick recap about the different shapes of your cubic functions. Okay, so now going back to this diagram that I have drawn here. Okay, how do I know that the x-intercepts here are 0, 2, and 3? We know that our x-intercepts can be found when y equals to 0, and when y is equals to 0, our x will be equals to 0, x minus 2 is equals to 0, otherwise x minus 3 is equals to 0. Since they have already given it to you in factorized form, it is not difficult for us to know that the intersections will have to be 0, 2, and 3. So now that we have drawn out the diagram, it is easier for us to know how to interpret the area that we need to find. This is essential because if I do not have the diagram, I would not be able to know whether this area is below the x-axis or above the x-axis. Because if it's below the x-axis, I have to apply the negative sign, okay, to make the area positive. So now, okay, proceeding to find out what is the area. In this very first step here, I have to integrate from 0 to 2 for the equation of the curve. Take note that I have used the expanded form, okay, because with the factorized form of the cubic function, I cannot actually go about doing my integration. So I integrate from 0 to 2, and this actually is my area over here. While this negative integration from 2 to 3 for the cubic function is actually referring to, maybe let me choose a different color. It is actually referring to this part over here. Okay, so then now we can actually simplify, substitute in the values. So for the very first definite integral, we are actually going to have 8 over 3 minus 0, while in the second definite integral, I will be having 9 over 4 minus 8 over 3 after I substituted in the values. So then I do my calculation using my calculator, and I will have the answer 3 and 1 over 12 units square. I hope you're able to understand this solution here. We will next take a look at finding the area of a region between a curve and the y-axis. So what this means is that we want to find out what is the area from the curve towards the y-axis over here. So previously, when we did our definite integral and relating it to area of a curve, we were looking at the area below the curve, okay, in this manner, from values, let's say from A to B, okay, whereby I will be looking at integrating A to B, some function with respect to x, okay, and this function over here, okay, is usually in terms of x. Because if it were not to be in terms of x, then we can't be integrating with respect to x, right? So now that we want to find the area between a curve and the y-axis, which is over here, we will actually be integrating with respect to y. So in order to integrate with respect to y, okay, our function over here must be in terms of y instead. Okay, please pardon me for my poor handwriting. Okay, so since we're integrating in terms of y, then the values here must be of the y-axis. Okay, so That's why I'm taking the value C and D from the y-axis. And then I have to ensure that the equation of the curve that I'm given, I make it such that, I manipulate it such that I have, let me erase this first, I have x as the subject so that I can have this expression to be in terms of y. And then I can put it inside my definite integral to solve. Okay? Let me illustrate this concept to you using this example here. So in try 10, we want to find the area bounded by the curve y equals to 4 over x squared. The y-axis, the lines y equals to 1, which is this line here, and the line y equals to 4, which is this horizontal line here. Okay, so this diagram actually very nicely have shaded it and to indicate for you that this is the area that we want to find. Okay, so in order to solve this question, what I mentioned earlier is that given this equation of the curve y equals to 4 over x squared, we will have to be integrating with respect to y. So I have to do my manipulation such that I make x the subject. So in this section over here, okay, what I'm trying to do is to make x the subject. Now observe that in making x the subject, okay, at this step, I have x squared equals to 4 over y. So since I want x to be the subject, I need to take square root. Okay, and when I take square root, I will be having a positive square root here as well as a negative square root. Okay, I'm sure you're wondering why is it that I do this rejection. Okay, this expression here is for x. Okay, so x is either positive or negative. But if you look closely at the diagram given to you, this curve is in the x-axis region whereby they are actually positive value. Okay, so my x values for this curve is actually positive. So there's no way for us to have negative x values. Okay, so I need to draw my conclusion based on context of the question. Alright, so therefore, in finding the area, okay, I will integrate from 1 to 4, taking the y-axis value, for the function 2 over y to the power of half, because I applied this here, with respect to y, okay, and then I just apply my usual integration for algebra. Okay, there's no difference in integrating in terms of y or integrating with respect to x. Okay, it's just a variable, it's just a letter itself. So I will have 2y to the power of half, because negative half plus 1 will give me half. Then not forgetting to bring down the power of half over here below in the denominator. Okay, then I am having 4 and 1 over here. Then I will simplify, so I'll get 4y to the power of half, okay, because 2 divided by half is 4. So then substituting in the value of 4 into y and the value of 1 into y, I am looking at 8 minus 4 for this definite integral. So it simplifies to 4 unit square. And that's how I get my answer for try 10. Let's move on to take a look at try 11. Okay, so we are given this diagram which shows the region P bounded by the curve y equals to ln x, the x-axis, and the line x equals to 2. So x equals to 2 is a vertical line. Find the area of the region P. Okay, as much as we like to, based on our conventional understanding or our intuition so far, in order to find this area of the region, our intuition is to integrate ln x, okay, because this is our equation of the curve, from 1 to 2, okay, that means that we are going to have a definite integral like that. But the problem here is, how do we integrate the logarithmic function? Okay, in case you have forgotten, we cannot integrate the logarithmic function. We can, however, integrate maybe 1 over x dx to get a ln function. Okay, so but then I cannot integrate a ln x with respect to x. There's no such rule for us to integrate. Okay, So then we have to look through the different kind of skills that we have actually acquired. So this question is not very intuitive. Let me show you the answer. The strategy for this question is to find out the area of the rectangle. Okay, so the area of this rectangle here, and minus the area of cube, which I have highlighted in green. Okay, so why is it that I'm doing this? Because if I have y equals to ln x and I try to make x the subject, which is in this process here, I am going to realize that I will have e to the power of y. And we do have the necessary skills in integrating e to the power of y. Okay, so this is the strategy behind solving this question. So in finding out the area of Q, I need to actually find out what is this value here, which we know that is 0, and then it's going up to ln 2. How did I get ln 2? Because at this point of the curve, when x is equals to 2, substitute it into the equation of the curve, I will have y equals to ln 2. Okay, so area of the rectangle will be length, which is 2, okay, 2 units for length, which is this length here. Okay, and the breadth is actually ln 2 units. Okay, so from 0 to ln 2. So this is the area of the rectangle. Let me just indicate it for you. And then we minus away the area of region Q, and that will be to integrate e to the power of y from 0 to ln 2 with respect to y. Okay, so integration of e to the power of y remains the same as e to the power of y. Okay, and then substitute in the values and you simplify it. Okay, e ln 2, by the way, is the value of 2, and e to the power of 0 is the value of 1. So I can have 2 ln 2 minus 1. Okay, you may want to leave your answer exact if the question asks for it. Otherwise, leaving it to 3SF and not forgetting the units, okay, is also acceptable. Right? This is a very interesting question. I hope that you appreciate this strategy, okay, in solving to find the area of a region when you are given, okay, the curve equation to be in terms of to be in a logarithmic function. Let's now move on to question 9 found in your exercise 17.2, your textbook page 132. Okay, this question is rather interesting, so let's read the question first. The diagram shows part of the curve y equals to fx, so there is no function given to you exactly. There's nothing for you to exactly integrate. Okay, so given the points P, Q, and R, which all lie on the curve, we want to find out what is the value of the integration, okay, from 3 to 6 for y with respect to x, and 2 to 9 for x with respect to y. Okay, so there's a lot of understanding that we need to apply over here. Okay, so take note that this is with respect to x, but then this is in terms of y. Okay, then also this is with respect to y, but yet this is x. So what's going on? Okay, so what we have to understand over here, okay, is that with respect to x for y, this y actually could be your fx. Okay, because y equals to fx, right? And then this x, okay, is probably when you make x the subject, okay, from your y equals to fx. Okay, so this is just to get you to have the understanding here. Okay, so now 3 to 6, what is exactly this area that we're referring to? Okay, so since we're looking at with respect to x, that means this value 3 and 6, they are found on the x-axis itself. So x is equals to 3 is here, while x equals to 6 is over here. Okay, so strictly speaking, okay, the area, let me just erase things, or maybe let me just choose a different color. Okay, this part here of this definite integral actually refers to this area. Okay, And then the other integral from 2 to 9 with respect to y. Okay, that means that our 2 and 9 are actually values found on the y-axis since we're integrating with respect to y, right? Okay, so 2, oops, I'm sorry. Okay, 2, y equals to 2 is actually here. And y equals to 9 is actually here. So, okay, since we're integrating with respect to y, this is the area that we're looking at. Okay, so in this question, essentially, what the entire expression is asking you to do is to add up the green area with the purple area. Okay, so how are we going to do this if we don't even know what is the function in the first place? Okay, we can use some simple understanding of rectangles to actually solve this question. So let me just clean up this diagram, okay, for us to have a better idea. Okay, so what we're doing is that we are going to find out, we draw this meter. Okay, what we will do, what we want is actually this area that I've shaded, this entire red part. Okay, so what we can do is to find out the area of the big rectangle here, followed by subtracting the area of this smaller rectangle here. Okay, so the area of the big purple rectangle that I have drawn a parameter around, okay, as well as to minus away the area of the green rectangle. And the leftover will be the area, or rather the answer that we want to find to this question. Right? So let me show you the answer. Okay, so big rectangle, which was the purple one that I mentioned just now. So this is the big rectangle. So I have my length to be 6 based on the x-coordinate of r, and then the breadth here to be 9 because of the y-coordinate of r. Okay, so 6 times 9 will be the area of the big rectangle. Then we want to minus away the area of the smaller rectangle, which is here. And this length here will be based off the x-coordinate of p, which is 3. And then, oops, I'm sorry, okay, the y-coordinate, the graph over here will be based off the y-coordinate of p, which is 2. Okay, so that's why I have a 3 times 2 over here. So the area of the big rectangle minus the weight area of small rectangle, and I will be getting 48 units squared. Right, this is another strategy behind finding out the definite integral value without even knowing the equation of the function. Right? We will now solve our final question, which is try 12, found in your textbook page 130. In this question, we want to find the area of the region bounded by the coordinate axis, the line MN, and the curve x equals to 2y squared plus 1. There are a few ways to approach this question. I'm only going to show you one way. You can go and think about how to solve it, okay, in another way. That's my challenge to you. Okay, so this is the area that we want to find. And in order to do that, okay, my solution is going to propose, okay, finding out this area and adding up with this area here. Okay, so in order to do this, let me just use a different color so that we can see it better. Okay, so in order to do this, I need to think of what are the things that I'm missing first. Okay, so I need definitely this value. Okay, because what I'm going to do in figuring out the red area is that I need to actually integrate this straight line with respect to the y-axis, with respect to y. Okay, so the next thing that I need is actually the equation of this line. Okay, so I need the equation of line, I need this y-axis value here. Okay, then in order to do that, I can actually find the y-axis value by knowing what is the intersection point. Okay, right? At this juncture, maybe you are wondering, why do I need to find equation of the line to find out what is this area? This is also area of a triangle one, right? So I can do half times base times height, which is definitely possible. Okay, all right, but I'm just going to propose to you a very generic way of solving. Okay, so regardless of whether it's a line or a curve, you will definitely be able to go about solving it. Okay, so you can do area of a triangle as well. All right, then so now let's proceed with the answer, shall we? Okay, so the first thing that I needed to find, or rather there were a few things that I needed to find just now. Okay, so let me just write it out over here at the top. Okay, I need to find the equation of line MN as well as the intersection point of line and the curve, so that it can proceed to let me know what is this value here. Okay, so let's find out what is the equation of the line MN. All right, since we are given the coordinates M and N, I can find the gradient. Okay, then I can find the equation of Mn, which is y equals to negative x plus 4. How do I get this so easily? Okay, take note that M is actually the y-intercept value of the, or rather the y-intercept section point. Okay, so I can know what is the y-intercept value here for the straight line. So therefore, y equals mx plus c will tell me that the c value will be positive 4. Okay, otherwise you can use your usual conventional method. That's perfectly fine as well. Okay, then now I proceed to find this intersection point. Okay, so we're done with the equation of line. Okay, so intersection point, we substitute in equation 1 into equation 2. Oops, I'm missing a step. Let me just do some rectification. So my equation 2 is actually my curve equation. Okay, so substitute in, and I will be able to simplify to arrive at a quadratic equation. I can factorize this, or you may want to use your x formula. That's perfectly fine. And I have x equals to 5.5 or x equals to 3. Okay, notice over here that I rejected this x equals to 5.5. Why did I do that? Okay, so again, it's due to the context of the question. So this intersection point, if you look closely to the question, okay, it happens here. And it is actually before your point N. And point N has an x coordinate of 4. Okay, so surely this value here must be lesser than 4. Am I right? So therefore, between 5.5 and 3, I will have to reject 5.5 and accept x equals to 3. Okay, so that's how I go about rejecting x equals to 5.5. Okay, so let's move on to the second page of this question. So I just put in summary over here. I have already gotten my equation of the straight line. Okay, and I know that I have x equals to 3 over here already. I need to actually find out what is this y value here. So I substituted x equals to 3 into my equation of the line. Okay, it's slightly easier to solve that way instead of substituting into the equation of the curve, which is going to be quite a hassle. So y is equals to 1. Okay, then y is equals to negative x plus 4. That means that if I make x the subject, I will have negative y plus 4. Why do I make x the subject? Because if you recall earlier on, I wanted to integrate, okay, the line over here from 1 to 4, okay, in order to find out what is this area of the triangle. So this is the part that I'm getting at over here. So this is the area of triangle. Okay, so the alternative is that I can do half times base times height. So depending on your viewpoint, okay, I can have my base to be 3 and my height to be 3 as well, because 4 minus 1, okay. So let's just put it clearly, 4 minus 1. And I actually will get half times 3 times 3, that's 9. So 4.5. Okay. And actually, if you check in with this calculation, 8 minus 3.5 is indeed 4.5. Okay, so just an alternative over here. Okay, then going back to finding out what is the area of this part. So I'll integrate the curve here from 0 to 1. Okay, this is easier because I already have x, the subject, so I did not have to do any manipulation. So therefore, I am integrating from 0 to 1 to y squared plus 1 with respect to y. So I'll just label this loosely as the green area. Okay, then I do my integration, substitute in the values. Okay, and my final answer will be 6 and 1 over 6 units squared. Alright, I hope that you are able to understand this solution. Okay, I challenge you to think about this area in a different manner and see whether you are able to get the same answer or not. Okay, and that's it. We have come to the end of chapter 17.2. So with that, there is homework. Okay, exercise 17.2, textbook, page 132 to 133. Please complete questions 6, 10, and 11. The deadline will be on 23rd June, Wednesday. Please submit it onto Google Classroom. Okay, that's all. Thank you, everyone. Bye-bye.